Hi guys, this is the Ceyear mid-high-end signal spectrum analyzer. It uses 11.6 inches capacitive touchscreen. The forefront and rear handle design make the transportation easier. The abundant external interfaces can greatly shorten the test process. On the right of the screen are the system-level menus. On the top are the main setting menus. There are also some hard keys and a knob and some arrows on the right of the front panel. This new 4052 series spectrum analyzer covers up to 50 GHz. The current one is 40 GHz model. This series features 1.2 GHz analysis bandwidth and excellent phase noise and dynamic range. We can press the bottom left system button and check the About. This table lists all the installed options for the current device. Today, I will show you how to use the devices to make normal spectrum measurement, pulse measurement, 5G NR measurement, and phase noise measurement. Firstly, we click plus to select the measurement options. These functions depend on the options you selected. Here we choose spectrum analysis and then choose the sub-function of ACP measurement. We press New button to create the ACP measurement screen. We choose back to the normal spectrum analyzer. We can press the frequency, amplitude, bandwidth on the top to change the measurement setups. Here we can use our finger or the hard keys or the knob to change the RBW. We rotate the knob clockwise to increase the RBW and counterclockwise to decrease it. We can see the sweep speed at 30 kHz RBW with 40 GHz span. We keep decreasing the RBW, 10 kHz now. We set the span to 200 MHz. And keep decreasing the RBW to 5 kHz, 3 kHz, 1 kHz. We change the vertical scale to 15 dB per division. Now we keep decreasing the RBW, 500. 300, 200, 100 Hz. Now we set the signal generator's output to minus 120 dBm. The noise floor is too high and there is no signal detected. We set the RBW to 50 Hz. No signal. To 30 Hz. There's still no signal. We set the span to 20 MHz to speed up the process. Now the RBW is set to 20 Hz, to 10 Hz now. We can see the weak signal now. We press peak to find the signal at 123 dBm. We further decrease the RBW to 5 Hz, and the sweeping speed is even lower now. But the 20 GHz weak signal is more obvious now, and each peak remains at about minus 123 dBm. Secondly, we set the signal generator's frequency to 1 GHz and turn on the pulse modulation. The pulse width is 5 microseconds and the period is 20 microseconds. We enable the output. We set the spectrum analyzer's RBW to 1 MHz. The span is full span now. To check the details, we set the center frequency to 1 GHz and span to 100 MHz. We set the referencing level to 0 dBm. we change the span to 1 GHz, 2 GHz to check the pulse spectrum. Now we press the plus and create a pulse analysis window. The time domain wave is not stable because of the poor trigger. We have to press trigger and set the trigger mode to power. Now we get a stable pulse in the time domain window. We can double-click the sub-window to display it in full screen. But there is only one pulse in the window. We set the stop time to 100 microseconds. And now we get 5 pulses now. These ISO-defined pulse parameters are listed in this window. We can see the average power, peak power, pulse width, rise time, fall time, and other time or power parameters. A pulse train can also be analyzed. In the signal generator, we set a pulse source to a multi-pulse, a pulse train. This is a predefined pulse train file, and we can edit it freely. We can see there are 6 pulses with different widths and period. We press Save and Apply to enable the pulse train. The trigger mode is still set to power. We set the stop time to 130 microseconds and set the trigger hold off to 101 microsecond. Now we get a relatively stable time domain display. We can see the 6 pulses now. The 1, 2, 2, 6, 8, 12 microseconds with pulses. The pulse parameters details are listed here. We can see the pulse widths are exactly the same as the generator's setting. Thirdly, in the generator side, we take on the 5G NR and close the pulse modulation. We enter the 5G NR setup screen. We select to generate the TM3 and score 1 downlink model at 1 GHz. In the analyzer side, we select the 5G NR downlink analysis. The frequency is set to 1 GHz. In measurement configuration menu, we filter out the TM3 and score 1 model and choose the same configuration. We can see the 64 ohm signal and the EVM is 0.40%. Let's choose another model to demo the 5G NR test. We cancel the model filter and now in the full list we choose the third one. Again, in the measurement configuration menu, we find the same model and record the corresponding setups. The QPSK signal is identified and the EVM is about 0.28%. Because the current analyzer is only 40 MHz analysis bandwidth, we have to choose the 5G NR model with lower modulation bandwidth. Lastly, we set the signal generator to 1 GHz analog output. The output power is 0 dBm. In Analyzer, we press plus to select the phase noise measurement mode. We set the carrier frequency to 1 GHz. The start offset to 10 Hz. Set the stop offset to 100 MHz. Now we get the 1 GHz signal's phase noise. Actually, the phase noise of our signal generator is much better than the displayed.